Okay, let's continue our discussion about covalent bonding. And what we're going to do is start drawing what we call Lewis structures or dot diagrams to illustrate how electrons are shared in this process. So it says, remember the octet rule in ionic bonding. Basically, what the octet rule says is that atoms want a full outer energy level. Now, octet means they want 8 electrons in that outer energy level, but we know there's a lot of exceptions to that. All right, so how do we do this? What we want to do is draw dot diagrams, and you know what those are, to illustrate how compounds or how substances covalently bond together. So let's take hydrogen, which has 2 hydrogen atoms. What you're going to do is draw each hydrogen atom, and then you're going to put your dot there representing the 1 valence electron of hydrogen. Now, hydrogen is either going to want to give away an electron or take an electron. It's not going to want to do both things. So it doesn't make sense that this one would want to give and that one would want to take or whatever. So what they do is they get close together, and what they do is they share each valence electron with each other. What that means is picture that pair of electrons in between, and this hydrogen has a hold on those electrons, and this hydrogen has a hold on those electrons. So picture them both grabbing onto those electrons, and that is what keeps those hydrogens together, and we get what we call a hydrogen molecule, or a hydrogen diatomic. So what we'll say is that line there represents a shared pair of electrons. So a shared pair of electrons, which we are going to refer to as a single bond. So if you have one shared pair of electrons, that's what we're going to call a single bond. All right, we're not going to worry about the box diagrams. We're just going to focus on the dot diagrams. So let's take fluorine, for example. One fluorine has 7 valence electrons. So another fluorine has 7 valence electrons. So again, the same thing. Fluorine is definitely not going to want to give up an electron. So what these things are going to do is move closer together, and they're going to share that valence electron with each other. So again, this fluorine has a hold on those electrons. This fluorine has a hold on those electrons. So each of them holding on to it is what makes that single bond happen. All right, so let's talk about unshared pairs. So we have these pairs of electrons on the outside of the fluorine symbol. When you have 3 pairs listed like that, what you can do is one of 2 things. Actually draw them there, or not draw them there. When you have an atom and you know that there's valence electrons there and there's 3 pairs, you don't have to draw them. They're implied. On the other hand, if there's less than 3 pairs, so let's say less than 3 pairs, then you draw them. And we'll show that in some examples a little bit later. All right, so let's talk about some terms and then do some more examples. So a single covalent bond, like we said, is one shared pair of electrons. An unshared pair is, for example, that fluorine where you have a pair of electrons not involved in bonding. It's that simple. All right, let's take a look at a couple of molecules here. We'll take a look at water and ammonia. So water is made up of hydrogen, oxygen, and hydrogen. So as you can imagine, you're going to take 2 hydrogens, each with 1 valence electron. And then you've got your oxygen with 1, 2, 3, 4, 5, 6 valence electrons. So those hydrogens scoot on over, and then they share their valence electron with oxygen, which shares its valence electron with hydrogen, and you end up with 2 single bonded hydrogens. Now, when we talk about something called VSEPR theory, what we're going to do is we're going to draw the water molecule like this. Now there's less than 3 unshared pairs, so we want to draw those. So what I'm going to do is I'm going to draw them on top of the oxygen like that. Don't worry about why right now. We'll deal with that later. Ammonia, which you will eventually memorize, is NH3. So again, we're going to take nitrogen with 1, 2, 3, 4, 5 valence electrons. Each hydrogen with 1 valence electron. So we end up with nitrogen, single bond to hydrogen, single bond to hydrogen, single bond to hydrogen, and a lone pair. Alrighty, let's move on. Let's keep moving so we don't make the video too long. So let's draw some dot structures for the following compounds. Alright, so again, what you want to do is 2 things. You want to write the element symbol, figure out the valence electrons, and draw that many dots. And we have Cl, 1, 2, 3, 4, 5, 6, 7. So those 2 come together to form HCl. Now again, I can put those 3 pairs there, or I can leave them out. I would recommend at this point putting them there until you get more comfortable with it. I2, Cl2, and Br2 are all going to do the same thing. You have 2 Cls, or 2 Brs, or 2 Is. Each of them have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So each of those is going to form, whoops, a single bond with the other one. So again, I could draw those lone pairs in there, or unshared pairs, let's call them. Lone pairs or unshared pairs, it doesn't matter. The Br2 would do the same thing, and so would the I2. So you can do those on your own and then ask in class if you have any trouble. All right, let's take a look at H2O2. So we have 2 hydrogens and 2 oxygens. Now you want to be careful. Hydrogen can only fit 2 valence electrons in its outermost shell since it's in the first energy level. So hydrogen is always going to make only 1 bond. So that hydrogen is going to bond to that hydrogen will bond to that oxygen. And then we just want to make sure that each oxygen has the correct number of valence electrons, which is 6. So if we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, that would make sense. So we'll draw this structure, and we'll actually draw this structure a little differently later, but we can draw it like that for now. PCl3, same idea. If you look at phosphorus, count up its valence electrons, count up chlorine, count up its valence electrons, you're going to end up with phosphorus, single bond, single bond, single bond, and then you would put in those lone pair of electrons. All right, so the lone pair of electrons, again, those are electrons that are not involved in bonding. So this compound would have this structure would have 1, 2, 3, 4 pairs of lone pair of electrons. Bonding pairs, there's 2. And unshared pairs of electrons, we can say that those are basically the same thing as lone pairs. What we will also talk about is lone electrons. So let's say you just have 1 hydrogen atom with 1 electron there. That is what we would call a lone electron. And we'll talk about that in more detail later. We're going to call those things with lone electrons, we're going to call them free radicals, sorry. 2 things. I almost forgot, and then my video was jumping a little bit. So we're going to call those free radicals. All right, let's move on. Again, I'm trying to keep these videos under 15 minutes. All right, let's take a look at double and triple bonds. So here's what you're going to do. To do these structures, let's say you have oxygen, and you have 2 of them. What you want to do is count up the total valence electrons. So each oxygen has 6. So we have a total number of valence electrons equal to 12. So what you want to do is put those around the structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But what you want to notice is that this oxygen, even though it can claim these 2 electrons as its own, 2, 4, 6, it's only got 6 valence electrons. So what we'll do, and we'll do this in more detail later, we're going to take 2 of those electrons and we're going to put them there. And again, we'll go over how you do this in more detail a little bit later. So what you end up with are 2 shared pairs of electrons, which each oxygen can count as its own, and we're going to call that a double bond. So a double bond is when you have 2 shared pair of electrons. Carbon dioxide, the same thing. It's going to share 2 with that oxygen and 2 with that oxygen, and then the oxygen will have 2 lone pairs. And again, don't worry about how I'm doing this right now. We're going to go over that in more detail. But those 2 would have 2 shared pairs. When we look at nitrogen and carbon monoxide, what you're going to end up with is 3 shared pairs and 2 lone pairs. So we're going to call that a triple bond when we have 3 shared pairs of electrons. So we could draw that like that. Carbon monoxide would then be that with the lone pairs. And again, just to emphasize, we're going to talk about how we do that in much more detail. All right, let's move on. We just want to talk about a couple of things real quick and then we'll wrap it up. All right, so coordinate covalent bonds. What we're going to say is a coordinate covalent bond is a bond where one element supplies both bonding electrons. All right, so what does that mean? Let's say we have an NH3, and we drew the structure for that earlier. And there's that lone pair of electrons there. Well, let's say we have a hydrogen, which is a 1+ charge, so it has no electrons. So that hydrogen wants 2 electrons. So what it's going to do is it's going to get closer to the NH3, and then, whoops, I don't know what that is. So then what it'll do is it'll share, or actually, it's going to borrow those 2 electrons. And then what we're going to end up with is NH4, and that whole thing is going to have a +1 charge. And what we're going to do is we're going to call that a polyatomic ion. And basically what it means is when you have a whole group of atoms, nitrogen and 4 hydrogens, bonded together and the whole thing has a charge. So poly meaning many, many atoms that act as an ion. And again, I know I keep saying this, but we'll talk about that in more detail a little bit later. You can look at the carbon monoxide example in your book and the BF3 boron trifluoride in the book also. All right, so it says draw the electron dot structure for the following. So we have a couple of examples here. So what we want to do, again, if you have H3O+, and that's made by taking an H2O and an H+, that means we're going to have H bonded to oxygen, bonded to another hydrogen. And then if you take an H+ and bond it to there, you're going to have what we call an H3O+ ion. And that whole thing is going to have a charge of 1 plus. And what we're going to have is a lone pair of electrons there. So again, we're not going to worry too much about this at this point. What you want to recognize is the examples that H2O molecule is supplying both bonding pairs for that third hydrogen. So we're going to call that a coordinate bond. So anyway, what you can do, I want to keep this under 15 minutes. So what you can do is look at these examples in the book and then see if you can draw those on your own. And if you can't, we'll do them in class together. The other thing you want to look at is table 8.2 on page 234. You're going to have lots of examples of these structures. All right, so let's just define some things quickly. A single bond is one shared pair of electrons. and you draw it with a single line. A double bond is two shared pairs. You draw it with two lines. And then a triple bond is three shared pairs, and you draw it with three lines. Two things you want to know about single, double, and triple bonds. Single bonds are the longest. Triple bonds are the shortest. In other words, the distance between two atoms is the longest with a single and the shortest with a triple. A single bond is the weakest, and a triple bond is the strongest. And that should make sense. Three things bonding as opposed to one. All right, you've got the homework here, and again, notice it's not all the problems. So look at those problems in the book, do those. I'll have a link on Canvas, and you can submit those, and we will fix up any details in class. All right, that's all, folks.